We saw in our last video that voters exercise a great deal of strategic effort when deciding whom to vote for. A voter has to weigh how well a candidate's stances match with their own against that candidate's likelihood of defeating another candidate of primarily opposite stances. This strategizing is an inevitable outcome of a simple first-past-the-post election system. On the other hand, the instant runoff system puts that strategic brainpower to use. In an instant runoff election system, a candidate must obtain more than 50% of the population's votes in order to win. To accomplish this goal, voters are asked to rank their preference for each candidate. At the close of the election, the first-place votes are counted. If a candidate has more than 50%, they are declared the winner. But if not, the candidate with the fewest votes is removed from the race. Then, any voters who voted for that candidate have their second preference votes assigned. It's as if a runoff election were held based on the information that the voters have already provided. This process is reiterated until a candidate receives more than 50% of the votes. In this instant runoff system, a voter can still think strategically about which opposing candidate they want to see defeated, but they don't have to worry about wasting their vote on a candidate who has little chance of winning. In today's video, we'll implement an instant runoff system in our election simulator and see how it impacts the results. The first thing we'll have to change to implement an instant runoff system is in the voter class. Instead of giving the voter just one vote, we're going to give them a vote list. This is where we're going to store all the information about their preferences for each candidate. And in order to do that, we're going to populate this list with a new type of item called a vote. So each vote that the candidate gets, so this is one line on the ballot of, I prefer this candidate number 1, this candidate number 3, this candidate number 11 billion, etc. I suppose that would be one way to eliminate a candidate would be to just put, Avogadro's number next to their name. What this stores is the candidate that they're considering, so the candidate on the list, the match score that they assign, so this is the same match score that we've been calculating before, and then the rank that gets assigned. Now, this rank is initially going to be 0. We'll have to determine that later. The way we determine that is with a new function called sort preferences. So we've got a few new things here at the front end of the code. This sort preferences takes in a voter's vote list and loops over them and does the same type of thing we've seen before with this in greater search. So basically we're looking for the number of candidates that had a greater match score than the current candidate being considered. So we're comparing vote against vote 2. So we're comparing the candidate in vote 2 to comparing the candidate in vote to the candidate in vote 2. There's no need to compare a candidate against itself, so we'll skip over that part here. And so here we're checking whether vote has a score that is less than vote 2. If that's the case, then that means there's one more in the set of the rest of them that's greater than the score in vote. So we increase in greater by 1. And then we assign the rank as that number that is greater. And just for it to make numerical sense, we're adding a +1 here so that 1 corresponds to it. So if there's none greater, then that is rank number 1. If there's 1 greater, then that is the second place rank number 2. If there's 2 greater, that is rank number 3, etc. If there's N candidates, that's going to be a total of N candidates for the rank. So the ranks go from 1 all the way down to the number of candidates. Then we need to sort the votes. And I know there are more efficient ways to do sorting. I've never really studied sorting. That can be a topic for another video sometime. Besides which, these lists are not that big, so I'm not going to get that big a payoff by doing something fancier. So we're just creating a temporary list here. We'll loop over the entries in the vote list here, and basically we'll assign each one of them to their appropriate spot. So basically, if that vote's rank is equal to the current step, then we append that vote to the list at that point. So that way, temp list now has rank 1, then rank 2, then rank 3, then rank 4, then rank 5, etc. And then all we have to do is return this list. So we're going to overwrite vote list with this temporary list here. for water break. Drink your water, kids. So that takes care of all the changes we need for the voters. We don't really need to change anything about the candidates. We're still counting votes for them. I've decided to go with we're going to do indem equal 3 for right now. And I've decided let's do an incomplete list of voters, or excuse me, an incomplete list of candidates. So we're not going to explore these possible combinations. This is just to make the election a little bit more interesting, because now there will be folks who have their views definitely unrepresented. We come down here. We've got the voters randomly distributed again every year. We'll change that in just a minute to take a look at it. To confirm that this is working, I've set in years equal to 1, and we'll only do, I think it's 10 voters, just to bit more manageable. Let's see, our match score calculation still goes the same way, except that now what we do, instead of just evaluating whether the match score is greater, which I guess means I don't need this max score here anymore. I can get rid of that, I think. Search for max score. That's it. Okay, good. So now instead of recording the match score, instead of comparing the match score, we're going to record each candidate's match score. So we're appending to each voter's vote list this new vote item of canned match score in 0. And I think that ought to be fine because we do. Oh yeah, we clear the list of voters every year. Sorry, I had a momentary confusion as to whether I was appending more and more stuff every year, but we reset the voters every year. That's right. So we assign them, we record which candidate they're considering, which match score is associated with that candidate, and we're initializing the rank to 0 because we haven't done the sorting yet. Speaking of sorting, here we are. So after we've looped over the candidates, we can sort that voter's preferences. So this is that voter recording their list of preferences on the ballot with a 1, 2, 3, 4, 5, etc., instead of punching out a single hole in the ballot. And so next comes the instant runoff. This is the most complicated part, meaning it's the one that took me the longest to create, but it should be pretty straightforward to read through. So the condition, there are many conditions to evaluate, so we're just going to summarize all those in whether we are done. So we are not done originally, so done equals false. We need to keep track of which candidates have been dropped. And so that initially starts as an empty list because no candidates have been dropped. We're going to keep track of the round number just in case. Down here we'll have if we exceed the number of possible rounds. So if we end up dropping all the candidates, or if we keep dropping the same candidate over and over again, then something went wrong. I did need this debugging earlier, although it doesn't pop up now. But if it does pop up, then we know something went wrong because it says something went wrong. So what we do is, what we're looking for now is, instead of looking for the candidate with the most votes, which is first past the post system, we're looking for the candidate with the minimum number of votes. So we'll initialize that value to n voters. We'll loop over the number of candidates. We're going to set the candidates' votes to 0 each time, so we'll recount the votes each time. That's really not entirely necessary, but this thing was already layered enough as it is. And like I said, with only a handful of candidates, it's not going to take that long to recount everything. So then we loop over the voters. And what we have to look for here is whether that voter's next choice has been dropped. So, for example, when we start out in the first loop, there's nobody in dropped candidate, so this is not going to happen. So rank is going to stay equal to 0, and the voter will add to the candidate's vote their top choice. So their top choice, they get to add their vote to. Once we have candidates in the drop candidate list, though, this while loop is going to increment, and it's going to add 1 to the rank every time. So if your rank 0 candidate, meaning your top choice, is in the dropped candidates list, then your votes get assigned to, then you increase the rank by 1, so you go to your rank 1 candidate. If that person is not in the dropped candidates list, we move forward, so your votes get assigned to your next choice. But if your second choice is in dropped candidates, I'm very sorry. Then we add another one, and so it's your rank 2 choice that gets the votes added to it, et cetera, all the way down until the last one in the list. Although it shouldn't come down to that, it should always come down to the second to last one in the list. Because at that point, one of the two must have more than 50% of the vote. So then we loop over the candidates, at least the ones that are not in the dropped list. And so I've got this print statement in just so we can keep track of each round of how the votes are being assigned. And we check for the winning condition. So if one of the candidates has more than 50% of the votes, then we can declare the winner. We are done. We don't need to count anymore, because once one of the candidate has more than 50% of the votes, it's not possible for anybody else to get more than 50%. Otherwise, if we're not done yet, if we've still got a split vote and there's not a majority winner, a true majority winner, then we drop the lowest voted candidates. So what we do is we evaluate whether that candidate has the fewest number of votes, and then we basically drop that candidate. So we record that candidate in this variable drop, and then we add that candidate to the dropped list. Once that candidate is in the dropped list, it gets ignored in all these other lists up here. And so each round will tell us, the code will tell us which candidate has been dropped, and then we continue to increment until we are done. And so then at the end, we, I guess I don't need this max votes anymore either. Sorry, I was so excited to get this done. I did not do a whole lot of cleanup. Let me see. I don't think I need to do that because I've already declared the winner. Okay, give me 1 second. I did not realize I forgot to clean this up. All right, so then we're going to say candidate name. Oops, no, not like that. Oh, actually, do I want to do it that way? No, I don't want to do it that way, because I'm already printing the number of votes. All right, present election results. Winner.win. All right, so we've already declared our winner. Right, okay. So we'll say print winner.name has won. There we go. Okay, sorry about that. Clean up there. And then we're still calculating the average and graphing the population satisfaction. And then what we have to do is we have to reset everything. So we have to reset the candidates' votes, etc. We've been doing that. That's right. So what we'll do is we'll run 1 year. So we're going to run just a single year with 10 voters just to see how the numbers pan out. Now, as a reminder, we've got an incomplete basis set of candidates, and so some voters are going to be unhappy and have to go with their second choice. It's just going to have to happen. Okay, so let's take a look at how this works. So we've got round 1. Sue got 0 votes, 2, 4, 2, 1, 1, etc. So in order for somebody to be declared the winner in a 10 voter population, this thing has 10 voters and 1, 2, 3, 4, 5, 6 candidates. That is a sad state of affairs. Somebody's got to get 6 votes, right? Nobody has 6 votes, so nobody is declared the winner. By the way, you notice, look who's suddenly getting votes. Tom's getting a vote. How about that? Well, that's great. So Sue has the fewest number. She's got 0, so we drop Sue from the list, which means in round 2, when we go to evaluate, we've got 1 fewer candidate. We don't have Sue. Who did Sue's voter end up going with? 4, 5, 6, 7, 8, 9, 10. 2, 4, 2, 1. Oh, Sue didn't have any votes, so she doesn't have any votes to get reassigned. Oh, I guess if somebody gets 0, I can drop them and the next lowest one. Oh well. So in the next one, we've got this distribution. Now this is where it faults a little bit because I should be dropping Jim and Tom from the race. because they've each got 1. But don't worry, that'll get taken care of soon. It drops Jim just because he's first in the list. And the person who voted for Jim had a second choice of Deb, because I can see that Deb's votes increased by 1, going from 4 to 5. Good job, Deb. You're getting one step closer to winning. Then we've got Tom needs to get dropped because he's got 1. See, that ends up getting taken care of anyway. And so Tom's vote, their second choice, was also Deb. And so Deb ends up winning. Not terrible. Now, that would have happened anyway because Deb had 4 votes. But you imagine if these folks' second choice had been Bob instead, then Bob would suddenly have 4 by the end, and Deb would have 4, and it would be up to John's voters to decide how to split their vote between Deb and Bob. Did I say John? I think I meant Bob. Either way. So it can end up being a little bit different than that. Let's see, when we re-randomize, let's see how it turns out differently. Deb wins again, even though Deb is not the clear... So Deb doesn't have a clear majority here. Deb ends up winning here just because she's people's second, third, or fourth choice. Let's run another one to see. Okay, in this one, John wins. So we take a look at this one, for example. John is tied here with Deb at the beginning. John doesn't even collect any extra votes until round 4, it looks like. And so by round 5, John has accumulated enough to have a majority. So let's do this. Let's increase. Let's see how this performs over time. So let's increase our number of voters. Where are you in voters? There you are. So let's give this 100 voters now. And let's run it several years. Let's run it over the course of, let's say 20 years. So 20 election cycles with an instant runoff system. I should also mention, in addition to being called instant runoff, it's also called a distributed preferences system because you are distributing the preferences of the voters. There we are at 17. Okay, there we go. So let's see. So we get the distribution of preferences like we had before. Let's take a look at just the 20th election just to make sure it's working with the larger population. So Tom has 3 votes. Those votes end up getting distributed. You notice they don't all go to the same place. One of them went to Deb because she goes up by 1, and 2 of them went to Jim. As we go forward, so now Sue is going to get knocked out of the race. Sue's got 15 votes, so those votes get distributed among here. Ooh, none of them go to Deb. Wow, Deb, you were not popular among Sue's supporters. You end up with Deb dropping out of the race, and you end up with Jim winning here, which is interesting because Deb was the leader in the beginning, and Jim was actually tied in the middle at the beginning. So even though Jim did not have a clear lead there, so in a first past the post system, Deb would be declared the winner. But Deb did not have enough support among the rest of the population. Jim ends up collecting that support, ends up being the winner down here. And so that's a major difference between a first past the post system and an instant runoff system. Let's see. You also notice that we're sharing the winnings a little bit better. Let's run this over more years. Let's run this over, Let's run this over 200 cycles. And let's, for this thing to run a little bit faster, let's not print who we're dropping and what the round results are. Okay, so we come out to the end, and we've got a little bit better distribution of our wins. So we've got Sue, Deb, Bob, and Jim winning about equally. Tom, I'm sorry to say, just doesn't seem to win. Good for you, Tom, for sticking around all 5 of these videos. John only takes 3%. I'm not entirely sure why that is. If is he duplicated with somebody? No, I think he's just, I think he's not different enough from the other folks to stand out in that sense. So we see that this is more equally distributed. This hasn't really impacted our value for overall satisfaction. Our standard deviation is about the same. Our graph still has this X shape to it. Of course, running with 3 dimensions, those are going to be pretty spread out. I wonder if we were to go to just 2 dimensions. Let's see how that impacts those results. So we'll still have 10 issues per dimension, and so I need to take out a couple of candidates because they'll be redundant. So I have so I have plus minus. I got another plus minus here, so let's comment out John. Got a minus plus 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 minus minus 0 0. Okay, so I only had 1 extra. 1 2 3 4. Yeah. So let's run this one, see what we get. Okay, so we do end up with a little bit better distribution. Okay, so I think I was right that John was not, John or Deb wasn't unique enough among the others. So we end up with a little bit more equal distribution among the winners. Our standard deviation is a little bit bigger, so that's kind of nice. This is actually more, is that more spread out? It's at least not less spread out, I don't think. Been interesting to see. An instant runoff system is definitely interesting to model and watch develop, and it's sort of the mathematician's delight because you get to do all these different predictions, you get to do all these different strategies. It's definitely a lot of fun to work with. Do I want to? All right, cut here, Brian. Do I want to make the? Actually, yeah. Oh. Stay cut, Brian. Stay cut. Alright, minimize. Alright, let's make one more change. I would like to see how this goes with a non-uniformly distributed voting population. So what we're going to do is we're going to go back to the spoiler effect code. We're going to take our voter generator from here, and we're going to put that outside the loop. Here we go. And so we're just going to do 1 year because with the same population, the results are going to be the same every year. And let's take out our voter generation here. 3. There we go. And then let's just do 2 dimensions again. Okay, I've already got it at 2 dimensions, and we'll do 100 voters. So 31% are going to be in the -1 quadrant. 15% are going to be in the. Oh dear, I had those. Oh, excuse me. I'm looking at the wrong number. So 31% of those are going to be in 1 1. 15% of those are going to be in -1 1. 29% are going to be in -1 -1, and the remainder is going to be in 1 -1. So we've got a majority in 1 1. Let's see if that majority can hold in a distributed preferences system. We got year equal to 1. Yes. All right. Let's run this. Nope. Voter underscore list is not defined. Oh yeah. Voter underscore list equals empty set. There we go. All right, try again. Oh, right. I need to actually, I I need to go back and print the distribution. I forgot to put back in the interesting part. All right. Print the round winner. Print who got dropped. There we go. One more time. Okay, so this thing proceeds through 4 rounds. Bob has the majority at the beginning with his 31 votes. Tom has to drop out of the race because he has 0 votes. It's at this point that we need to drop Deb from the race. Okay, her votes go to Bob. And then, some of her votes go to Bob. Some of them go to Jim. And then Sue has to drop out of the race, and hers split between the two. So we end up with Bob and Jim as our finalists. Bob and Jim did hold the majority at the beginning. Let's play around with... Let's see. Let's give Bob... Bob is the one with the lead. Yeah, let's give Bob a little bit less of a lead at the beginning. Let's put him at 0.30. Oh, that's only going to be 1 fewer vote, isn't it? Well, maybe that'll make a difference. Nope, sorry. Well, Jim is 1. Oh my, that made a huge difference. Wow. Okay, so we changed 1 voter. In a 100-vote system, in a 100-voter world, we changed 1 vote, and we went from Bob winning to Jim winning. Let's see, Jim is -1, and Bob is 1-1. So I guess we will conclude this series by saying that, yes, 1 vote can, in fact, make a difference. Wow, that is fun. I think that's a good note to end on. Thank you so much for watching. I will see you next time. Bye-bye. Thank you for watching this video series. It's been a fun excursion outside of my field. Before we close, I want to point out that in all the simulations we ran, we assumed 100% voter participation in the election. Despite gains in the last 2 decades, the United States has a voter turnout rate of less than 50%. And while disillusionment with politics and government is certainly one factor, and voter registration laws are hotly debated, there is one significant hindrance to voter turnout that remains unaddressed every year. Our election day is on a Tuesday. Although there are historical causes for why this is the case, there is no good reason for this practice to continue. We know that most people are freer on the weekends than they are on weekdays, and holding elections on a Tuesday instead of on a weekend benefits no party or interest group. It just doesn't make sense. If this resonates with you, head over to whytuesday.org for more information or to see how you can help address this issue.